I should say here that this is a kind of pattern that I use. The pattern that I use is that on the flanking boards there'll be an outline. That the outline is going to cover the major ideas that we'll talk about that day, and it does a couple of things. First, it looks an awful lot like the objectives that you'll see in the ebook. Sometimes there's some variability, sometimes there's not, but it's the major ideas we're going to cover. It keeps me on track. I can see what has to be talked about, and it gives me sort of a template to work from. But I encourage you to spend some time writing this down, and each of the lectures will start with a brief discussion of this material, and we'll touch on the high points of the lecture from these outlines. One of the secrets of any lecture, of any course that's given, is that the number of ideas in any given lecture is fairly small, 6 or 8 at most. That's a big number. And those major ideas will be covered in the outlines. And if you get to the point where you can write down these outlines, if you get to the point where you can read the major ideas on the outline and talk about them off the top of your head, you're getting yourself familiar with the material. You're getting to the point where you're fluent with the material. You're getting to the point where you can talk about it and you're prepared for the exam. So these are, I think, are useful both to me and to you. What we'll do today is we're going to talk about water. We're going to spend a little bit of time on the components. We all know that it's H2O, but those components are organized in a particular way. There are covalent bonds between the oxygen and the hydrogen. And because of those covalent bonds, the electrons are being shared. And it's the peculiar way in which these electrons are shared in water which allows water to be liquid at room temperature. And if you've been following some of the space exploration stuff that's been going on in the last few years, you'll know that one of the major emphasis of the rovers on Mars is to see if there's water. Is there water there? Was there water there? If there was, then maybe it's compatible with life. The whole idea of those missions is to determine whether life ever could have existed on that planet. If you look at the Kepler images, Kepler is looking for planets that are rotating around stars many, many light years away. But there are certain rules about how far from a particular star the planet can be in order to have liquid water. The assumption is if we're going to find life on other planets, it will be based on liquid water. And the reason for that is because everything we know about life on this planet revolves around water and salt solutions. And water, the peculiarities of water allow it to permit life. And we'll talk a little bit about those peculiarities. And one of the things I'll point out in passing is that we're going to compare water, which is liquid at room temperature, and has a boiling point of 100 degrees, has a freezing point of 0 degrees, with the gases in air around us. The gases that we're sitting in air, are 79% nitrogen, 21% oxygen, and yet it's a gas. The molecular weights of oxygen and nitrogen are 32 and 28 respectively, and yet they're a gas, and water with its molecular weight of 18 is liquid. Why is that? And we'll see it has to do with something called hydrogen bonding and the sharing of electrons in those molecules. But in addition to water being liquid, it also provides a medium into which we can have salts go into solution. We often refer to water as the elixir of life. It's the elixir of life because it's a salt solution, whether we're talking about the fluid inside cells or the fluid surrounding cells. It's a salt solution. That means that ions need to go into solution in water, and it's the peculiar characteristics of the dipole moment on water which allows ions to go into solution. Now, when we think about this, first we'll talk about the role of charge. We'll talk about the role of the dipole moment in water. We'll talk about something known as the shell of hydration. That means each of these ions will be surrounded by a sphere of water molecules oriented to either the negative anion or the positive cation. The other idea that's going to come out of this is that when we put ions into solution, they then can be moved around in solution by thermal activity. They can move from place to place. They can take a random walk, depending on how they're being bounced around by the water molecules. And this bouncing around determines a kind of random walk of these ions. And the idea of the random walk, the idea of things going to randomness, the idea of entropy is really, really important in biology. And much of biology, much of life, is using various chemicals, various energies to harness the energy of the random walk. It doesn't matter whether it's the random walk of ions moving across membranes in neurons or moving across membranes in muscle, or whether it's the random walk of carbon dioxide and oxygen diffusing from blood to the air in your lung or from your lung to the blood. It's a random walk. It's the randomness that's important here, but we have to harness that difference in concentration, and we'll talk about how that gets done.